So we are familiar with the idea of percent. Percent means per 100. And so when we find a decimal, then we multiply that by 100 to see what that percent is. So we say times 100% to get what percent it was. You can essentially do that with all of these others. So for 1,000, instead of multiplying by 100, we'd multiply by 1,000. Parts per million, we would multiply, I'm going to just write 10 to the 6th. This is 10 to the 9th. And this is 10 to the 12th. So we just do that. Since these vary by 3 in their exponent, and this one too, because this one's 10 to the 3rd, then if I'm going from one to the other that are right next to each other, I can again just move that decimal point by 3. The reason we use these is because sometimes when we have, like when I first had that number that was 0.000001, that was just a lot of zeros to be looking at. Well, when we are talking about things that we don't want in the air or things we don't want in the water, we want the concentrations of those things as small as possible. So we want to be able to detect them in parts per billion or parts per trillion. So if something's really bad for me, I want it to be in a really, really small number, parts per trillion. If something's kind of bad for me, I'd want that more like parts per thousand, because it's just not realistic to get it real low. So lead in our water, we want that pretty low. We usually measure that in like parts per billion. Something like copper, it's okay if we have a little bit of copper in our system, but too much is bad for us. So we might measure that in parts per million instead of parts per billion. So if something is 0.005 parts per 1,000. Now, usually this will be PPT and this will be PPT, and you just have to know from the context which one you're talking about, but I'm going to try and keep the TH for 1,000 and TR for trillion. So this is 0.005 parts per 1,000. How many parts per million is that? So going from 1,000 to 1,000,000 is 3 orders of magnitude. Okay, and so we are just going to move this 1, 2, 3, or we can say 0.005 parts per 1,000 times 1,000 parts per million in 1 part per 1,000. And that is equal to 5 million. Okay, so you can go back and forth between those. What I would really like for you to be able to know is what parts per million, parts per billion, ppm, ppb stand for. Which one is bigger? So if I asked you on a multiple choice quiz, if something was 5%, 5 parts per million, 5 parts per billion, which of those is the largest amount? You would say, percent, 5% is a lot more than 5 parts per billion. So you should be able to compare those two. I'm not going to ask you to do the calculations because the calculations tend to be weird. What we tend to do is use a mass percent. So we're not looking at moles of iron. We use how many grams of iron, which is really weird because if we look at the periodic table, iron has a mass of 56, right? Lead has a mass of 207. So having the same ppb of those two does not mean having the same number of particles of those things. So it's kind of weird in that calculation. So we're not going to do the calculation, but you should know which one's bigger, which one's smaller, what does the M and the B stand for, okay? All right, last thing I want to look at is going back to mass percent. Empirical formulas. Remember that when you are trying to find the ratio of either elements or parts, what you want to compare is the moles. And so we need to find moles of each component. So if I had, let me see, if I had SO2, well, let me say I have SOX. And I know that this is 50% oxygen, so thus 50% sulfur. We know that we need to turn those to grams. And I had a handful of people that got grams and then started adding the molar mass of sulfur and oxygen together. But we don't know what the total molar mass of this is. So we can't do 32 plus 16 and start dividing by that because we don't know what that is yet. So what we want to do is convert each individual part to moles. So this is grams of oxygen. So we would say 1 mole divided by 16. This is grams of sulfur. So we would say 1 mole divided by 32.06. Okay, so you have to divide each part by the mass of that part, not by the mass of what you think the whole might be. So 50 divided by 16 gives us 3.125. And then 50 divided by 32.06 gives us 1.560 for the sulfur. And then what do we do at this point? We want a ratio of those elements.
Divide each one by the smallest.
Divide each by the smallest. So I'm going to divide this one, 1.560. That's going to give me 1. 1.560. When I plug that in, I'm going to get 2. And so I would have the formula SO2. Okay, so remember, don't divide by just adding the elements together. Divide by the individual element. All right. I will see you Wednesday. I will have your test back for you. If you need to be making something up for the test, let me know.